All right, guys. Again, happy water mean break day today again. We're going to do some differential equations here. It can be kind of a tricky topic. We're going to spend a couple days on it. So stick with it today and come in with questions tomorrow, okay? So looking at worksheet number 1 here, we're going to start off with just what a differential equation is. So a differential equation is simply a function in which the function is dependent, okay, dependent on its derivative. Okay, it's dependent on its derivative. So to get the value of the original function, we have to, or it's going to be dependent on what the value of the derivative is. We'll start off with some simple examples, and we'll get to maybe some harder ones. So if we know y, let's start with this. If y prime is equal to 2, what must the function y be? All we're doing is taking the integral, the general integral. So y must be 2x plus c, right? We've done that plenty of times before. But how we're going to think about this differently now is I would ask you this question. Could you rewrite y such that it includes its derivative as part of the equation? Well, can we rewrite y? Well, if you look here, guys, I have y prime is equal to 2. Okay, y prime is equal to 2, and I have a 2 in that equation for y. So rather than write 2, I could write y prime because y prime is equal to 2, right? So I could rewrite this as y prime x plus c. Again, since y prime is equal to 2, those two things are equal. I should easily be able to replace the 2 with y prime. So I could think about y as y being equal to y prime x plus c. In this case, you can clearly see that y is dependent on the whatever the derivative of y is, times x plus c. And if we actually want to write this out, I wrote this on my solution key, right? Y is equal to its derivative, okay, times x plus c, right? Y is equal to its derivative times x plus c. All right, so given these conditions above, we found a general solution, y equals y prime x plus c. Typically, we'd write y equals 2x plus c, but technically, it's a function y that's dependent on its derivative. So given the conditions we found above, we found a general solution, one in which all the answers were encompassed. But if we wanted to find a particular solution, we would need a specific point, okay? So using the problem above, if y of 3 equals 7, find the particular solution to this differential equation, okay? Well, again, we're going to start with, we know that y is equal to y prime x plus c. And I know in this particular solution, when x is 3, y is 7. So I can say 7 equals y prime 3 plus c, and I also know that y prime is equal to 2, so I could rewrite it as y equals 2 times 3 plus c. You can easily see that c is equal to 1. So your solution would be y equals y prime x plus 1, or you could write it as y equals 2x plus 1. Now you might be saying, all right, well, does that just mean from now on, Mr. Botter, instead of writing the slope, we just write y prime? No, actually, in reality, you're not going to see many like this. And if the derivative is just a constant number, you're just going to write the number and not the derivative. But I did want to give you an example here where the derivative, okay, is part of the general equation. Because as we'll see in a second here, they can get a little bit trickier if you have x's and y's as part of the derivative, okay? So let's maybe just do one more quick example, and then we'll get into this idea called separation of variables. So if I told you y prime is equal to x, then y, okay, again, if we're trying to find its general equation, y is equal to 1/2 x squared plus c. And if you wanted to write it so that y prime is in it, right, we could write 1/2 y prime squared plus c. Okay, again, wouldn't normally write it that way, but again, just so you can see, we can write an original function where it's dependent on its derivative, okay? Number 2 is a little bit harder, okay? if y prime is equal to x times y, and this is really where all the work's going to come in, where most of our learning and is going to take place. All right, so when you see something like this where we have an x and a y as part of the derivative, we have to do something called a separation of variables. All right, so what we need to do here, okay, is we just need to separate, and you'll see how this is done in a second. We need to separate the variables first and then integrate. So notice when we did those answers or problems with x in them, we just simply integrated the function and got, for example, in the top problem above, 1/2 x squared plus c. We didn't have to do anything to the derivative first. In this case, since the derivative has an x and a y in it, we are going to need to separate those variables, okay? So I'm going to try to write out some nice clear directions here and steps that you can usually take every time. So the first thing when you see something like y prime equals x, y, and I want to know what y is, it's the first thing we need to do, okay? First thing we need to do is change y prime to dy dx. And you might be saying, oh, that's just semantics, Mr. Bodner. Do we really need that? Or some type of formality? Who cares? You'll see what happens. So let's just first rewrite the equation as, let me choose a different color, dy over dx equals x, y. Okay, so the first thing we're going to do, change dy over dx, or y prime into dy over dx. Step 2, okay, step 2, we're going to move, okay, x's to one side and y's to the other. Okay, so we're going to put all the x's on one side and move y's all to the other side. And if I do that in this case, I have to divide the right side by y and multiply the right side by dx. I get 1 over y dy equaling x dx. Okay, so again, you can see by separating y prime or replacing y prime with dy over dx, I can separate the dy and the dx from each other. Dy divided by dx. So I have 1 over y dy equaling x dx. Okay. So again, those are steps you're going to take every time. Change y to dy over dx, move x's to one side and y's to another. Step 3 is integrate. Okay? And by integrating, integrating is a function, it's like performing an action. And as long as we do the same action on both sides, it's something we're allowed to do. So what I could do, okay, is I could put the integral symbol over here and say, all right, I'm going to integrate 1 over y dy. And on the right side, I'm going to integrate x dx. And you can see now why we did those changing y prime to dy over dx. It allowed me to basically give directions. By putting that dy next to the 1 over y, it says, all right, integrate with respect to y. By putting the dx next to the x, it allows me to integrate with respect to x. Okay? All right, so step 3, I guess, was set up the integral by integrating. Now, for step 4, we're actually going to integrate. The integral of 1 over y, if you remember, is ln of the absolute value of y. Okay? And the integral of x is 1/2 x squared, but we need to put a plus c. Now c represents the constant. Now you might be saying, well, if we put the plus c on the right side, would we not need to put a plus c on the left side? Well, if we think about it, c just represents a constant. If I put a plus c, imagine me kind of squeezing a plus c over here. Now I have two constants. If I subtracted that plus c on the left and brought it over to the right, okay, I would have one constant minus another constant. But if you subtract that one constant from another constant, you're still going to get an answer of a constant. C just represents a general constant number. And whether you multiply that constant or subtract another number from that constant, you still just get a constant. So because C just represents a constant, okay, you only need it on one side. Okay, you only need that on one side. It just represents a number, a general number. All right, If that's a little bit tricky for you, I can talk more about it in class tomorrow. But in general, you only need one c. Usually we just put it on the side with the x, okay? Step 5, and this is our last step, is we're going to solve for y. And they might be saying, oh man, this kind of looks like a tricky equation to solve for y. Typically, in these problems where you have 1 over y, and that's going to be a situation that shows up constantly. So if you have 1 over y and you integrate it, you get ln of y. The way we can isolate y is basically take e, let me go back to green, take e, okay, and make ln of y the exponent. And if I do that to the left side, I have to do it to the right. So basically you make those exponents. And again, as long as you do it to both sides, that's allowed. E to the ln of y, if you remember your properties of exponents, if the base of your exponential and the base of the ln in your exponent are the same, it simplifies to whatever's inside those parentheses, which is just y. Okay, you can drop the absolute value at this point. The right side, I'm just going to say the right side guy could rewrite as e to the 1/2 x squared times e to the c, right? If you remember, if you multiply two things with the same base, it's the same as adding those exponents, right? So in this case, this e to the c is just a constant still, right? E is a number, c is a number, it's just a constant. So I could rethink of this e to the c as still as just c, right? Again, it's just a constant. E to the c would just be a constant number. So what I'm going to do, since it's going to be e to the 1/2 x squared times c, is I'm just going to rewrite it as y equals c times e to the 1/2 x squared. And that, guys, is our answer. You might probably sitting there being like, I have no idea what we just did. It's tricky, okay? But let's maybe just quickly review what we did. Okay, we started out and with this idea of, all right, I have this derivative. It's dependent on an x value and a y value, and I want to know what the original equation is, the general original equation, okay? Not a specific one, not at a specific point. What would a general equation be? Just like above here, we had y equals x, we come up with a general equation, okay? First thing we did, again, was change it into dy dx. As you can see, what did that allow me to do? The reason I did it is it allowed me to integrate over here with respect to each variable, one in terms of y and one in terms of x, right? I moved everything to one side. I integrated, okay? I took my general integral, only needed to add c to one side because c is a constant, okay? I made them the exponents, okay, and then simplified from there. So again, that y equals c times e to the 1/2 x squared is just a general, okay, equation where its derivative would be dependent on x times y, okay? All right, so that's a little bit tricky, but the good news is it's going to get repetitive a little bit, and that's going to make things a little bit easier. There's not a whole lot of differential, no pun here, differentiation between these differential equations. Not a lot, okay? There'll be some, but not a lot. So this pattern you're going to see hold up quite a bit. All right, so let's take a look, as I said, at some more challenging examples, but you'll see it's not maybe as bad as it may look. All right, so if we have, if y prime equals x squared times y, and y of 0 equals 1, find y of x, okay? They're asking us for the specific solution here, the specific equation where the derivative of that equation would be x squared times y. So let's follow those steps we did above. First thing we're going to do is change y prime into dy over dx, okay? And at any point, guys, if you think, hey, I think I got this, hit pause, okay? Try to work through the problem, and then hit play again and see if you get the same thing I do. If you want to walk through this one with me too, perfectly fine. All right, now we're going to separate x's to one side, y's to another. So we're going to get 1 over y dy equaling x squared dx. Oop, I wrote dy dx. Now we're going to integrate. Okay, we're going to integrate 1 over y dy. And we're going to integrate x squared dx. Okay, once we integrate, we get ln of y. Again, you can see this pattern. You're going to see that 1 over y a lot. Equaling 1 over 3 x cubed. And don't forget the plus c. We're then going to raise both sides. Okay, or make them the exponent. So we get e to the 1/3 x cubed plus c on the right, e to the ln of the absolute value of y on the left. Okay, we're going to come up here. The left side simplifies to y. The right side, again, you'll start to notice this pattern. I'll go through this pattern one more time. I could rewrite the right side as e to the 1/3 x cubed times e to the c. E to the c, again, is just a constant, so I could rewrite that as just c again. And I get y equals c e to the 1/3 x cubed, okay? But that's our general solution, okay? That right there is our general solution, and since they gave us a point, we need to find the specific solution. Okay, we need to find the specific solution, which means we need to find the value of c. All we're going to do is take the point and plug it in for x and y. So I have 1 equals c times e to the 1/3. Oops, I wrote double e there. E to the 1/3 0 cubed. 1 equals, what is that? C times e to the 0. E to the 0 is 1. So c equals 1. So my answer here, my specific solution, is y equals e to the 1/3 x cubed, okay? Again, what does that mean? That is an equation whose derivative would be dependent on, or would be x squared times y at the specific point. It would contain the specific point, y of 0 equals 1. Okay. All right. Why don't you try number 2 and then walk through, hit pause, okay? Okay, and then try working through that, and then hitting play and see if your answers match mine. Get as far as you can go, okay? And maybe let's start out with this. The sum of a function and its derivative is always 1. So I know this. This is my kind of starting point, that y plus y prime is always equal to 1. All right? So try doing that. See if you can get somewhere with that. Find the specific function. All right, hopefully you gave it a shot and you got somewhere. If you didn't get it completely, that's okay. But we're going to follow those same steps. We're going to change y prime into dy over dx. So we get y plus dy over dx equals 1. Okay? We're going to separate the variables. This one's a couple steps, so let me maybe do it a little bit slower. Dy over dx equals 1 minus y. And then I get, what do we get here? 1 minus y, oops, not 1 minus y, 1 over 1 minus y. Divide both sides by 1 minus 1 over 1 minus y. dy equals, you could really think about it as 1 dx. I'm going to integrate now. So we're going to integrate y, integral of 1 minus y dy equals the integral of 1 dx. If I integrate 1 minus y, it's a little bit tricky, but you get negative ln of 1 minus y equaling x plus c. Be careful with that integral. You're basically dividing by the derivative of the inside of 1 minus y, which would be negative 1. That's where that negative comes from. Now we're going to solve for y. Actually, before we do that, before we can raise it to the power, we need to move that negative over to the other side. So we're going to make it ln of 1 minus y equaling negative x plus c. You might be saying, well, why isn't it minus c? Again, guys, c is a constant, whether it's plus or negative. If c is meant to be negative, then it's going to come out to be negative. You're always just going to leave it as plus c. okay, and let the algebra or let the solving of C take care of whether it needs to be negative or positive. Don't force C to be negative. Okay, we're just going to leave it as plus C, and if C is meant to be negative 3, when we plug in our point at the end, C is going to come out to be negative 3. All right, we're going to do that same pattern of make the exponent. So we're going to get e to the ln of 1 minus y equals e to the negative x plus c. That simplifies to 1 minus y. All right, you've seen this trick enough. That's going to equal c times e to the negative x for that same reason above. E to the negative x plus c is the same thing as e to the negative x times e to the c. E to the c is just a constant, okay? So let's come up here. What am I going to do is subtract 1, okay, and divide by negative 1. Subtract 1 and divide by negative 1. Again, c just stays c. We don't have to change it to negative. Okay, but that 1, since that's an actual number, okay, is actually plus 1, not minus 1, sorry. When you subtract it over, it becomes negative 1, but then when you divide by the negative, it becomes positive 1. So that y equals c times e to the negative x is our general solution. To find the specific solution, let's plug in the point 0, 2. So we get 2 equals, okay, c times e to the negative 0 plus 1. Okay, e to the negative 0 is 1, so we get 2 equals c plus 1, or c equals 1. So my general solution is y equals e to the negative x plus 1. Sorry, not general solution, my specific solution. So my specific solution there is y equals e to the negative x plus 1. Okay, its derivative and the function are always going to sum to 1. Okay. All right, so here's what I would suggest. Let's just do one more. Let's do number 6. I know this video is a little bit long, but if this were a normal class, you'd have this for 50 minutes. We'll probably get done in, 27 minutes. So, it's about half the length of a normal class. So stick with it. I know it can be, these videos can be tough to work through sometimes. It can be kind of long. Hopefully it's our last one of the year and the last one of your high school lives. But, such is life. That's the way things go sometimes. All right. Population y grows according to the equation dy over dt equals ky, where k is a constant, and t is measured in years. If the population doubles every 10 years, what is the value of k? All right, so here's what we know, guys. We know that dy over dt equals ky. Okay, dy over dt equals ky. And we're trying to solve for k. Okay, we know that population y, it grows according to this equation. Okay, so what might be helpful for us in order to solve for k is to know the original equation on which the population is based on. Okay, this is the derivative of y, right? dy, the derivative of y with a relationship to t. It might be helpful for us to know what y is, what that population function is. That will help me solve for k. So to do that, we probably want to take the antiderivative. Again, though, it looks like I have a couple variables. This looks to me like a differential equation problem. We need to separate y and t, which you can't really see here, but you'll see how it works. We have dt, which means we need to separate these variables, okay? So what I'm going to do is move y over to one side and put the dt on the other. So I'm going to get 1 over y dy equals k dt, and again, k is just a constant. That's what we're trying to solve for. If I integrate both sides, I get the integral of 1 over y dy equals the integral of k dt. The left side is ln of the absolute value of y. The right side is k, my solution key is wrong. Should be kt plus c. If you're looking at my solution key, I wrote kx. It really shouldn't be kx, it should be kt. Ln of y equals kt plus c. Again, we've seen this ln of y a bunch. The way we're going to get rid of it, e to the ln of y equals e to the kt plus c. The left side simplifies to y, the right side, hopefully you've seen this enough now that you get it, that it's just c equals k to the t. That is my general solution. To find my specific solution, okay, think about this. This may go back to your knowledge of exponentials, but in exponentials, the value in front of your exponential term was always your starting value. And what was on the left side was your ending value when it came to exponentials. So that coefficient in front was what you started with, and the value on the left side of the equation is what you ended with. So I know if the population doubles every 10 years, if I just imagine, you could choose any number that doubles, but if, okay, my starting value or my C value is 1 and it doubles, that must mean my ending value is 2. So I can plug in 2 for Y, okay, and 1 for C. Again, those represent your starting and ending values in an exponential equation. Again, this is, I wanted to do this one as part of the video because that may be something A, you're not even familiar with, or maybe you learned it so long ago you're like, I never would have remembered that. Okay, but when exponential equations, that value, the C value in front of the exponential term, can always be thought of as your starting value, what you start with in an exponential term, and that Y at the end is what you end with. Okay, so I can do 2 equals 1, equals 1 times e to the k. K is what we're solving for. In t, it doubles every 10 years, so t is 10. Now this just is all what we need to do from here to solve it. It's just going to take a little bit of algebraic skills and some calculators. So if you don't have your calculator, you'll need to grab that out. 2 equals 1 times e is just, right, that's e to the 10k. The way we're going to isolate k is log roll this bad boy. So we get 10k equals ln of 2. Divide each side by 10, and 10k equals ln of 2 over 10, which if I'm rounding or truncating is 6.93. Okay. All right, hopefully that gives you kind of an introduction to this. Again, tomorrow we're not doing anything new, so we'll go over any questions that you might have. Your homework, if we scroll, why don't you guys try, okay, 1, 2, 3, and 4. Okay, those should be pretty, I say basic. They're going to follow all the same patterns we've seen. So just be careful. Be careful on number 4. That's not going to be the case where you raise each side or make each side the exponent with e as the base at the end. That could be a little bit tricky. And then let's maybe do number 8. So 1, 2, 3, 4, and number 8. Okay, number 8. Again, we're a half hour into class. Hopefully you can start it now and get most of it done, if not all of it done. Come in with questions tomorrow in class. We'll maybe do a couple problems from this that we didn't get to today, and then maybe do some AP problems, okay? See you guys.